Alright, welcome back. This is Engineering 101, Lecture 6, I'll get that right one day, Part 1. So this was the last lecture given on the day for enrollment withdrawals, which is now passed, hence this slide. And previously we've been talking about logic operations and bitwise binary addition in the Wednesday lecture. And so in this re-recording, we're going to go through signed binary and binary subtraction. And then we're going to start talking a little bit about the little man computer. So what we've seen in our discussions on binary so far is that there is a number of different ways to encode decimal numbers with binary equivalents. So the example on the slide at the moment, the unsigned 4-bit binary numbers from 0 all the way up to 15. You see, but using 4 bits, we've got 16 possible different values that we can encode using 4 bits of binary with numbers 0 all the way up to 15. And that's a reasonably consistent encoding strategy. There's a few reasons why this works, but in general the really simple one is that if I get 5 and I add it to 6 using bitwise binary addition that we did in the last lecture, we get 11, just like we would with decimal addition. And that's one of the real core take-homes from here. The ability to do addition and subtraction is key to a good encoding system. But the big drawback for this is that it means we can't encode any negative numbers. And in fact, we could use this exact same set of binary numbers to mean anything we'd like at all. So here's an example encoding system that is terrible. It is just nasty. It's got positive numbers, it's got decimals, it's got the letter Q, it's got the same number encoded multiple times. Addition doesn't work, it doesn't seem to follow any logical structure, but it is still an encoding system. However, perhaps a better way of doing it might be using something like a sign bit. So a sign bit is a very simple idea, which is just that instead of using the most significant bit, the 4th bit, to signify a number, you use it to signify whether the number is positive or negative. So using exactly the same numbers as we did in the previous slides, we can give them a different meaning. So if we use this meaning, all we do is we can count from 0 to positive 7 and from negative 0 to negative 7, just by using the binary bit. So essentially, if that 4-bit number starts with a 1, it's negative. If it doesn't, it's 0. Now this is a pretty simple encoding system, and it's pretty rigorous. It follows a nice logical structure, but it's not perfect. It has a couple of pretty terrible flaws. The first of which is it counts 0 twice, and it has negative 0. Neither of those are particularly great things. It means we've got room for another number. We may as well use it to encode another number, but we don't in this encoding scheme for whatever reason. And the second and more concerning thing about this particular encoding scheme is that addition still doesn't work. Let's take, for example, 2, which in this encoding scheme would be 0, 0, 1, 0, and negative 2, which in this encoding scheme is 1, 0, 1, 0. So recall, if we have positive 2 and we add negative 2 to it, that's the same as saying 2 minus 2. So if we add positive and negative 2 together, we should get 0, right? The same for positive 3 and negative 3, positive 4 and negative 4. So what happens when we add positive 2 and negative 2 together in this particular notation? Well, 0, 0, 0, 1 and 1 is 1, 0, 0, 0, 1, 0, 1. Oh, we've got positive 2 plus minus 2 has now given us 12. Sorry, that's a negative sign in this encoding scheme. That officially is encoding minus 4 in this encoding scheme. So while it does follow logical structure, our arithmetic has gone completely out the window. So we've encoded 0 twice and our arithmetic doesn't work. So how can we fix that? Well, the current system that best fixes this, so that addition and subtraction still work the way that you expect, is what's called 2's complement. So here's the whole setup for 2's complement notation for signed binary. So the numbers from 0 to positive 7 are exactly the same as they were in the previous slide, just using the sign bit. So essentially in 2's complement, if the most significant bit of your number is 0, it just encodes a normal, stock standard, unsigned binary positive number. The catch is what happens when it starts with a 1. Now that 1 is practically a sign bit. just like it was in the previous question. But what you'll notice is that the values of those numbers are no longer the same as their equivalents whose most significant bit is 0. So for instance, 1111 now encodes for -1 rather than -7, which is what it did in the previous encoding scheme. And the reason this is really nice is that all of a sudden our subtraction works. And we're only counting 0 once. So let's try that example again. So what we had before is we had positive 2, 0, 0, 1, 0. It's positive 2. And then now we have -2. In this encoding scheme, that is 1, 1, 1, 0. So what happens when we add those two together? -2. So you see, what we expect is to get 0, 0, 0, 0 along the bottom. 0 plus 0 is 0. 1 plus 1 is 1, 0. 1 plus 1 is 1, 0. 1 plus 1 is 1, 0. But because we're stuck in 4-bit, we get left with those numbers and our carryover goes away. So as long as we lose our number as long as we know how many bits our 2's complement is, and as long as we discard that carryover 1, our sum and subtraction now works. And if you haven't quite figured it out yet, this is exactly how we do subtraction with binary numbers. We don't. We do bitwise addition, and we encode negative numbers using 2's complement. So how do you get 2's complement? Let me give you an example like I have on the slide. So if we start with -5, let's say we want to find out what is the 2's complement for -5. We start out with what is positive 5 in normal 4-bit binary. So positive 5 is 0, 1, 0, 1. To convert to -5, so to figure out what the 2's complement is of positive 5, so what is the binary number that will signify -5, there's 2 steps. We flip all the bits and then we add 1 to the result. So step 1 is flip all the bits, 1, 0, 1, 0. So flip all the bits is kind of obvious. You flip a 0 to a 1 and a 1 to a 0. And then step 2 is add 1 to it. So if we get that and we add 0, 0, 0, 1, our sum is 1, 1, 0, 1. So this is -5 and 2's complement. This is positive 5 and 2's complement. So long story short, if we add those two together, we should get 0. The really cool thing about this process, the flipping of the bits and adding 1, is that if we start with -5, doing the same process will take us back to positive 5. So not only is it really easy to start with a positive number and figure out what its negative equivalent would be, it's really easy to start with a negative number and find out what it encodes by going back to its positive counterpart. So let me give you an example. Remember that -5 in 2's complement was 1011. So let's say I didn't know that. What I can tell from this number is that because it's in 2's complement, that bit there, because it's 1, I know that it's a negative number. But I don't know what negative number it is, because remember, with 2's complement notation, these last 3 digits here, they don't just convert into normal unsigned binary like we've seen so far. So what we do to find out what is the positive number this is equivalent to is we do that 2's complement. So first step, flip the bits, 0, 1, 0, 0. Second step, we add 1, 0, 1, 0, 1. And now this is equal to positive 5. So because the 2's complement of that number gave us positive 5, we know this must signify -5. Okay? You can just memorize a whole bunch of 2's complement negative notation numbers if you like, but it's far more efficient to remember the step of flip the bits and add 1, because going from positive to negative and negative to positive is exactly the same process. It's one of the best things about 2's complement notation. It's not the only 2's complement notation. There are a number of others out there, but 2's complement is the one where standard binary addition and subtraction work. So you might have a follow-up question, which is, okay, Smiley pants. What happens if we start with 0, 0, 0, 0? What is the 2's complement of 0, 0, 0, 0? Because if we flip all of those bits, we're going to get 1, 1, 1, 1, and if we add 1, we get 1, 0, 0, 0. So as per usual, 0, 0 equals 0, which is always a good thing for any encoding systems, and 1, 1, 1, 1 in negative binary is the minimum possible negative number. So 1, 1, 1, 1, and 4-bit 2's complement indicates -1. Okay. So just to take you through an example of using binary subtraction, let's say we had 5 minus 7. So let's say I wanted to do 5 minus 7 using binary. So first off, I figure out what is 5 in normal unsigned binary. 0, 1, 0, 1. We've done that before. And I want to take 7 away. So what I'm going to do is, instead of taking 7 away, I'm going to add -7. So I'm going to do binary addition, but find out what -7 is. So +7 in binary is 0, 1, 1, 1. Let's do the 2's complement, which is flip the bits, 1, 0, 0, 0, and add 1, 1, 0, 0, 1. So that means that is equivalent to -7 in 2's complement. So now I have 1, 0, 0, 1, and I do my bitwise addition as per usual, 1 plus 1, 1, 0, 1, 1, 1, and that is the sum of those two numbers. So what is that in 2's complement? Well, it starts with a 1, so that means it's a negative number, and so I'm going to have to do my 2's complement to figure out what it is. So first off, I flip the bits, 0, sorry, I said I'll flip the bits, 0, 0, 0, 1, and add 1, so I get 0, 0, 1, 0, and this is +2. Okay, so because I've got this and converted to that, I know this actually signifies -2, which incidentally, if you're following along, our original question was 5 minus 7, so we know it should be equal to -2. So don't forget with your 2's complement that if it starts with a 1, if the most significant bit is a number 1, then it does encode a negative number, and unless you know it off the top of your head, the best way to figure out which negative number that encodes is to do the 2's complement process on it, and that will give you the positive number equivalent. By the way, the thing that I haven't mentioned is that throughout this, that bit flipping process, that's actually the final important logical process that we haven't talked about yet, which is NOT. And NOT is really simple. It just means if your input is something, it changes the input. So if your input is 0, it flips it to a 1. If your input is 1, it flips it to a 0. So that's what a NOT gate does. If it's written out, you can see it like this. Sometimes it's represented as just a circle next to an AND or an OR gate. And that's it. So you should all be able to tell me what the 2's complement notation for a negative number is. For completion, you should be able to do binary-based subtraction, and for a challenge, you should have to think about how you might want to do binary multiplication or division. So we're going to stop there, and I will continue this lecture after the break when we talk about the little man computer.